In this lesson, we'll cover learning target number 6. So by the end of the lesson, you should be able to describe why most reactions occur in a mechanism, and you can also test a mechanism and discuss if a proposed mechanism is reasonable. Most chemical reactions do not occur straight from reactants to products, because they involve improbable collision events. Remember, in order for two reactants to do a reaction, they have to collide at the right orientation with the right activation energy. Achieving those three things becomes almost impossible if you have more than two reactants involved in the collision. A reaction mechanism is a series of steps that make up a more complex overall chemical reaction. For example, if we have a look at this reaction, I would have to have two NO2s collide with an oxygen simultaneously with the right orientation and all three particles with the correct activation energy. That is pretty tough to achieve, and that's why this reaction is improbable to happen in one step. Now, this overall reaction actually happens in two steps, and these two steps combined together are known as the mechanism. First, a single NO collides with an O2 and makes an NO3. Then in step number 2, that NO3 that just got made gets used by colliding with another NO, which decomposes into two NO2s. Each step in a reaction mechanism describes one molecular event or a collision, and each step is also known as an elementary reaction. You will notice that mechanisms contain chemicals that are made in one step and used in another and don't show up in the overall reaction. Our example in the above mechanism was NO3. These chemicals are called reaction intermediates. Now, determining the mechanism that a reaction uses is very tricky. Chemists try to find mechanisms by proving the existence of intermediates. The easy ones are the intermediates that have a distinctive color. For example, if both of your reactants are clear and colorless, and then you see a brown color formed, and then it disappears in the process of making your products, then you know you have a two-step mechanism. Have a look at the example video on oxidizing tartarate. In order for a mechanism to be reasonable, it must pass these three tests. Test number 1, the steps of the mechanism must algebraically add together to give you the overall equation. Test number 2, the proposed steps must have probable collisions. The number of reactant particles involved in an elementary reaction is referred to as its molecularity. Chemists have noticed that unimolecular, or one reactant decomposing, and bimolecular steps, or two reactants colliding, are very probable. However, termolecular steps, three reactants colliding simultaneously, are very rare. And finally, test 3. The mechanism must support the experimentally determined rate law. This means that the overall reaction can only go as fast as the slowest step. This is tested by writing the rate law for the slowest elementary reaction in the mechanism and comparing it to the experimentally determined rate law for the overall reaction. They must be the same. To write the rate law for an elementary reaction, all you have to do is use the coefficients in the balanced chemical equation as the rate exponents. Many rate law experiments have been done using trials where one reactant concentration changes and the other one stays the same in order to determine the rate law of elementary reactions. And they all turn out to be the rate exponents matching the coefficients in the balanced chemical equation. Now for overall reactions, this is not true. You have to do the experiments like previously discussed. Let's have a look at example 1. The overall reaction here is bread plus heat plus butter produces buttered toast. And over here is the experimentally determined rate law. Now I'm going to propose the following mechanism, and we're going to use the 3 tests to see if it's reasonable. Step 1, bread plus heat produces toast, and that's the slow step. And step 2, toast plus butter produces buttered toast, and that's the fast step. Let's see if it passes test 1. Does step 1 and 2 algebraically add together to give us our overall reaction? Remember when we were algebraically adding equations through Hess's law? If you have the same chemical on opposite sides of the arrow, you subtract their amounts. If they are on the same side of the arrow, they add together. So here I have toast repeated in both of my equations. I have it as a product and I have it as a reactant, so they subtract and cancel each other out. I am left with bread plus heat plus butter produces buttered toast. So test 1 works. Now for test 2, I look at each individual step and determine their molecularity. Because in step 1 there's only one chemical, bread, then this is described as being a unimolecular step. Now, unimolecular steps are very probable, so that step passes test 2. Step 2, I have toast and butter. Because there are 2 particles here, this is classified as a bimolecular step. Bimolecular steps are also probable, so test 2 is okay. The mechanism seems reasonable so far. For test 3, my overall reaction can only go as fast as the slowest step. The rate determining step in my mechanism is step 1. It takes far much longer for bread to turn into toast than it is to butter it. If I write the rate law for step 1, it will be as follows. Rate equals K times the concentration of my reactants raised to their coefficients in the balanced chemical equation. Now because there is no coefficient in front of the bread, it is a first order reactant. Remember, that means if I double the concentration of the bread, then I would double the rate of making my toast. To pass test 3, the rate law for the slowest step has to match the experimentally determined rate law for the overall reaction, and in this example, it does. Therefore, the mechanism is reasonable. The intermediate in this reaction mechanism is toast because here it gets made and there it gets used in the next step. Try out example number 2 and example number 3. The answers will be in the next video.